In early calculus, continuity is often treated as a simple visual rule. We are taught that a function is continuous if you can draw its entire graph without ever lifting your pen from the paper. But that intuition falls apart the moment you look closer. Under extreme scrutiny of real analysis, the idea of tracing an unbroken line fractures. To analyze what actually happens in these chaotic mathematical spaces, we have to upgrade our toolset. We need a rigorous definition of continuity. The elementary concept of continuity relies heavily on evaluating simple limits. Those simple limits assume a function will behave predictably. They rely on the expectation that as an input gets closer to a target, the output moves toward a single destination. The friction occurs when that predictability vanishes. We need a reliable mechanism to evaluate functions whose behavior near a point becomes wildly unpredictable or infinite. In higher mathematics, there is an absolute prerequisite. Continuity is governed by the formal, provable existence of a limit. Without a verified limit, continuity does not exist. To establish that proof, we rely on two advanced frameworks. The first is Cauchy's definition, which utilizes strict spatial neighborhoods to establish topological rigor. The second framework is the sequential criterion. Mathematicians use this tool to determine exactly when and where continuity fails. Mastering and balancing these two frameworks provides the foundation for determining where and why a complex system fails the test of continuity. Let's build our model from first principles, starting with Cauchy's definition of continuity. To anchor this abstract concept, we will focus our analysis on a single specific coordinate, the point where x equals 0. This diagram shows a smooth function. Cauchy demands a strict boundary. We set a bounded neighborhood around the function's output on the y-axis with an epsilon bracket. This requires a corresponding input neighborhood on the x-axis, established with a delta bracket around 0. For continuity to hold true, a specific valid delta neighborhood must be proven. This creates a strict mapping rule. If you select any random input point within that x-axis delta boundary, its resulting output must land inside the y-axis epsilon bounds. If even a single point escapes the epsilon boundary, the limit fails. This spatial mapping actually guarantees an unbroken connection at that local point. Analyzing a single point is just the starting line. We have to transition this logic to a broader domain. We define open interval continuity by applying this rule to a wider area. For an open interval to be continuous, this mapping between delta and epsilon must hold true for every point contained within that interval. We expand the definition further to encompass closed intervals. The mapping rule must remain intact even at the exact boundary edges of the domain. Cauchy's topological rules guarantee that spatial boundaries are never violated across any interval, providing a formal definition for continuous existence. Now, let's look at why the standard arithmetical definition of limits that students rely on eventually reaches its limit. The baseline expectation is that the calculated limit of a function as x approaches a target must equal the function's actual value at that target. A critical failure point for this simple equation occurs when we introduce complex mathematical functions that begin to oscillate infinitely. Look at this high-frequency wave bounded between negative and positive 1. As it approaches 0, the waves become infinitely dense. Try to identify the limit as it zeroes in. The output smears across the vertical range. Because it refuses to target a single value, the limit officially does not exist. This oscillating state means the standard arithmetical equation cannot be used to verify the function's behavior at this specific point. Even Cauchy's epsilon delta mapping is difficult to apply here. Mapping clean spatial boundaries through an area of infinite oscillation is a significant practical challenge. When basic arithmetic fails and topology becomes computationally difficult, real analysis shifts toward a discrete, sequence-based approach. We solve this by introducing the sequential criterion, a method that uses individual points to probe the center of the oscillation. A sequence, in this context, is a countable series of steps approaching a target. The underlying rule of the criterion: if a function is continuous, all converging input sequences must produce converging output sequences to the exact same limit. To use this tool, we look for a contradiction to that rule. We select two input sequences, a blue sequence and an orange sequence. Both step toward the exact same x-axis target, converging perfectly on the origin. Tracking the blue sequence's outputs, they hit the curve and clearly converge at a specific upper target value. The blue sequence resulted in a definitive limit. Then we track the orange sequence's outputs. They hit the curve and converge at a distinctly different, lower target value. Comparing these two resulting output limits reveals a mathematical contradiction. The input sequences converge together, but their outputs split apart. Because of this split, the sequence of the function itself does not converge. This divergence of sequential outputs is the formal proof that the function is discontinuous at that point. This split screen illustrates the complete dual framework. Cauchy's role establishes the overarching spatial rules of the topological domain. The sequential criterion acts as the discrete detector for locating and proving discontinuities. Navigating real analysis requires both tools to handle varying levels of complexity. The sequential definition is particularly efficient because it bypasses the extensive algebraic lifting required by epsilon-delta proofs when dealing with erratic functions. In upcoming lessons, we will apply these foundational proofs to categorize the specific types of discontinuity. These same frameworks will also allow us to tackle the concept of uniform continuity. Mathematical rigor isn't based on the assumption that a curve is unbroken, but on having the tools to prove exactly where and why it breaks.